Hi, my name is Greg Wilkinson, and this is The Wonderful World of Modern Physics, where the theories are made up and the laws of physics don't matter. Today we're going to be talking about quantum computers. Ooh. So, say you want to rob the world. Easy, right? You just, hack in every bank account, steal their money, right? Sounds easy enough? No. Banking and other online accounts are protected by what is called public key encryption. More specifically, by using the widely used RSA scheme. The RSA scheme operates on the basis that classical computers have an extremely difficult time factoring large odd composite numbers. Now, a composite number is a positive integer that is formed by multiplying two smaller integers. In the RSA scheme, there's a public key which is used to encrypt a message, denoted as N, and a private key which is used to decrypt the message, known as P and Q. In the RSA scheme, the public key is the product of the private key, which consists of two very, very large prime numbers. I'm talking like very, 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 very big, like 10 to the 9 big. Even bigger than that, actually, like 10 to the 30. Who cares? Yeah, let's do that. In order to break RSA encryption, one must be able to factor the large public key into its two prime factors, which is actually extremely difficult and time-consuming for classical computers to compute. However, with the development of quantum computers, there may soon be possible a way to do this in a matter of minutes. But before I explain how quantum computers could be used to break RSA encryption, let's first learn how they actually work in the first place. So let's start off with classical computers. Now, classical computers perform operations using your regular 1 and 0 bits, which can also be known as on and off. Memory can be stored in the form of bytes, which is a series of 8 of these bits. And classical bits can be stored on a variety of mediums. So, you've got your regular punch cards. Remember these? No, you don't. You weren't alive when these were around. Maybe you were, Charles, but that's beside the point. Anyways, the equivalent of quantum computers is this. Where classical computers use ordinary bits to perform operations and store memory, quantum computers use what are called qubits, which can be a 1 or a 0, or a 1 and 0 at the same time. Wild. A qubit can be stored on a photon, nucleus, or even an electron. Some researchers are using the outermost electron of a phosphorus atom, even, as a qubit. Now you must be wondering, how do you do math on these things, solve problems, or even compute anything on an electron? Well, think about it this way. All electrons have a magnetic field, kind of like this bar magnet here. The bit, which will be put in a magnetic field, the field of this electron is referred to as the spin of a qubit, which is this field here. Now the bit, which when put in a magnetic field, will align with the field, kind of like how a compass needle will align with the magnetic field of the Earth. Neat. So in the aligned state, the qubit has the lowest amount of energy and can be compared to the 0 state. So I should have this upside down, but this is your 0 energy state, and this is denoted as it's your 0 equivalent pretty much for a bit. This is known as spin down in the quantum computing world. Equivalently, when it's in its highest energy position, it's known as spin up with a 1-bit equivalent. Now I know what you're thinking right now. Isn't this just the same as classical computers? You got your 1s, you got your 0s. Well, you're right, but there's actually more to it. The qubit can be in both states at once. 0, 1, 0, 1. You never know. Being that the electron can be in multiple spins at once. The electron is in what is called quantum superposition. It has two coefficients that represent the probability that you will find it in the spin up or spin down position. Now, you're probably even more confused. Don't worry, I am too. But get this. Even though the electron can be in different positions at the same time, when it's measured, it can only be a 1 or a 0. It's only going to be one or the other. You can't measure it in the spin, any other spin position. So think about it this way. Because a classical bit can only be a 1 or a 0 at once, it can only do one operation at once, whereas a qubit can do two calculations at once, seeing as it can be a 1 and a 0 at the same time. Think about it this way. Consider these 4 operations. Now these are both done on, this is assumed that you have a 2-bit computer. So a 2-bit classical computer can only check one of these operations at once, whereas a 2-bit quantum computer can check all of these at once. And this is due to the phenomenon of superposition. Now, the reason why quantum computers have their superior power is because of the way that bits work with quantum computers. So one equivalent classical computing bit is equal to 2 to the n bits. So, you've got your 8-bit computer. What's 2 to the n? Well, crap. I don't know. I use a calculator. I don't do this stuff in my head. So 2 to the 8, that's 256 bits. That's crazy, man. That's what is that? That's 32 times the computing power. That's nuts. That's crazy. Wild. So, now that you have somewhat of an idea of how quantum computers actually work and operate, which is only, to a certain extent of our understanding, you must be wondering, how does a quantum computer actually work? How do you program it? How do you read results from it? How in the heck does this thing actually work in real life? Well, there's a lot of problems with that that first must be addressed before building a quantum computer in the first place. The biggest problem with quantum computing is stability. It turns out that any sort of vibration, thermal radiation, or any other effects can upset the spin of an atom to the point where you cannot expect correct results at all from your quantum computer. Therefore, the atom must be cooled to the cool temperature of almost absolute zero to expect usable results. So that's the problem with quantum computers, really. It's decoherence. This problem has been solved, though, and rather than explain to you how to build a quantum computer, I'm going to simply tell you how one has been built already in the past, seeing as there are many different roads that you can take when designing a quantum computer or device such as this. So, in 2012, scientists from New South Wales developed a single-bit quantum computer, just 1 bit. Or rather, I guess in that case, it would be a single quantum transistor, which was made from silicon with a phosphorus atom bit, or a phosphorus atom qubit, rather. So what it really looks like is a big block of silicon with one tiny little phosphorus bit in there. That's all you've got. So how do you get it in there? How do you do it? It's crazy. Well, watch this. So what you do, you've got your giant vacuum. That works. That's a vacuum. And what they do is they layer up, atom by atom, silicon atoms. Now this is going to be the medium in which the bit is actually stored. So you layer up, layer by layer, until you're at the layer where you want to put your qubit. So then, once you want to throw your qubit down, you lay down a layer of hydrogen atoms. So there's simply a silicon-hydrogen bond holding them together. Then you come along and you zap it, put a little bit of voltage into it. And one of these is going to fly away. You have another one that flies away. Another one that flies away. You're left with an empty void right here. There's nothing there anymore. So pretty much you just got all these this reactive bond, the loose hydrogen bond, just hanging out. And it's just hanging out all loosey-goosey, and then what you do is you release phosphine gas into the vacuum, which will only react with the hydrogen. So then what happens is it reacts, and they strip away all the hydrogen, and you've just got this little phosphorus atom in there. That little guy right there. Then you're going to come over, and they're going to layer up more silicon atoms on top of that. More and more and more. And think of this in 3 dimensions, obviously, rather than 2. And that's it. You've got your quantum transistor, and it's just sitting in there. Now you're wondering, how do you program this phosphorus atom when it's all the way inside this silicon enclosure? You don't even know where it is. Well, it's as simple as making microwave popcorn. Well, that is, you use microwaves. Now, microwaves are shot at the transistor, and then using a single electron measuring device, which measures the flow of electrons on an atomic scale, it can then be observed which state the qubit is in, that is, spin up or spin down. Now this is nice and all, but this form of quantum computing does not open many doors yet. What still must be achieved is to increase the number of isolated bits inside the transistor while still maintaining a state of quantum entanglement, which gives quantum computing its power. Now so far the only commercially available quantum computer has been produced by Vancouver's Go Represent D-Wave company. How much does one of these cost? Well, it's Really not too much, actually. It's just, oh, let's just keep coming. Oh, crap. This thing owes, cost $15 million. Hashtag still cheaper than a Mac. Now, how does this all come together? What can quantum computers do that classical computers cannot? Why do we need quantum computers to be fast in the first place? Well, one application is in solving what may seem like a fairly simple problem that I mentioned before, factoring numbers. Computers have a ridiculously hard time factoring large numbers. I'm talking, like I said before, really, really large, like 232 digits long, which is actually the largest number that has been factored in the universe. Congrats, humanity. Remember that little bit about RSA encryption that I talked about? Well, here's where quantum computers could mess things up a lot, in a good way, or a bad way. Depends on what side you're on. So let's first explain RSA encryption with a practical example. So, Nima and Noah no hair there. Yeah, nothing at all. So, Nima and Noah are passing notes in class. However, Charles Hogue, their fearless physics leader, keeps intercepting the messages and reading them out to class. Haha, this is funny. But also embarrassing. They try basic encryption using a common encryption and decryption key, which involves relating each letter to an integer. So A is going to be 1, B is going to be 2, and so forth. And then you just multiply it by a common encryption key. Now Charles, being an aspiring cryptologist, is able to figure out the encryption/decryption key. Again, embarrassing. He reads the note out loud. Turns out Nima has a bit of a crush on Noah. Ooh. And so Nima and Noah figure out that the only way that their messages can stay secure would have to be to have a different encryption and decryption key, with the encryption key being commonly known, hence the public key, which we've heard before. In fact, anyone can send Nima and Noah a secure message by encrypting it using their publicly known key. They just hand it out to anybody. The first step to RSA encryption is to create a public key from the private key. So, you remember this. You've got your N, which is your public key, and your private key, which is your P and your Q. Now, this key can be distributed to anyone. Anyone can send a secure encrypted message to Nima and Noah, including themselves. The message is encrypted using an agreed-upon private key, C, which can be turned back into N. So, pretty much this is what they do. They've got C, which is the message that they want to encrypt. Or wait, no, it's M. I was wrong. M is what they want to turn into, they want to send that over a secure line. So, what they do is they send over C, which is equal to M to the power of E mod N, where N is P times Q. And now, let's see. So the message is encrypted using C. C is sent, and using the private key, C can be turned back into N. Now, I won't get into much detail about how this actually works. It's pretty crazy and really complicated. But the meat of the meal is that you need the prime factors to be able to decrypt the message back into it. Because this is what you do. You take C, you put it to the D. D is equal to e to the 1 mod that and that, where D is the modular multiplication inverse of E, obviously. And then, C, you just do a little fancy math, put it up to the E to the D, which we already know because we know the private key, and that turns it back into M. It's pretty complicated, but quantum computers are able to solve this using what's called Shor's algorithm. Shor's algorithm is a quantum algorithm that is an algorithm designed to be run on a quantum computer, which is used for integer factorization. Shor's algorithm is designed to be run in polynomial time. Specifically, it takes quantum gates of order using fast multiplication. The current state-of-the-art factoring algorithm, known as the general number sieve, works in sub-exponential time, which takes significantly longer for computers to be able to process. Now, this algorithm has already been proven to work, this polynomial one known as Shor's algorithm. and has been implemented on a quantum computer already. Now you ready for it? The best thing that this quantum computer has been able to do, the most complicated calculation it's been able to do, is the factorization of 21. That's it. 21 into 3 and 7. All of that. All the electron layering, putting that little phosphorus bit in there. That little guy. That was all to factor 21. I could have done that. Oh, anywho. That's how quantum computers work. I hope you had a great time. I did too. And I hope you learned something today.